watching Dr. Dot's Spectacular.
Frank Drake and I couldn't decide which of us were the oldest member on this panel, but as one of the older members, move it up. As one of the older members, I'm going to play the arch conservative on all of this. I want to say, I guess to start, that I do believe there's a fair chance we will see, we, not necessarily us as individuals, but that the human race will see conscious machines. I don't think, for a variety of reasons that I'm going to try to talk about, that it's on a 30-year time scale, and probably not, in my opinion, on a 100-year time scale. I guess I'll start by making one broad claim, and that is there are different kinds of problems, and some problems are not solved by throwing a lot of MIPS at them. And that the problems we're talking about now, in part...
Define MIPS, so not everybody knows.
Oh, millions of instructions per second. In other words, having lots of faster computers, there are a whole line of problems that we've had progressively faster computers and still have not solved. And in fact, if I draw a curve, we've heard a lot about exponential curves. If I draw a curve about the increase of computer power, and here I seem to be contradicting a bit about what Ray said, but when I draw curves on the increased efficiency or usefulness or flexibility of software, I get a very different kind of curve. It doesn't go up like that. Now, what I want to do is to start by simply giving, and most of you will have seen versions of this, but I want to start by giving you a bit of the background of what we're talking about, at least from the human point of view, when we talk about conscious machines. Let's see if I grab my pen out of my pocket. I've got something to point with. The central nervous system is made up of a bunch of elements called neurons. These neurons are intertwined. Often when we talk about these artificial neural nets, we ignore a great many of the properties of the neurons, and I've only put two up there. Neither of these is very simple to realize for an individual neuron. When they interact, we get things that don't look at all like what artificial neural nets do. A major feature known for over 100 years about the central nervous system is that it's highly entangled. That is, that there are lots of loops in this system. And if I pay attention to that a bit, we get to some points of comparison between standard technologies and what goes on in the central nervous system. And this at least should give you an idea of the complexity of the problem. First of all, each element in the central nervous system contacts somewhere between 1,000 and 10,000 other elements in the central nervous system. Our most complex machines that we build, typically the fan-out, this contact rate, is on the order of 10. Now, a close colleague of mine, Murray Gell-Mann, is fond of saying that when I go 3 orders of magnitude, I go to a new science. And so here is one 3 orders of magnitude effect here. A second thing, and these are the simplest points about the central nervous system. If I talk about the visual input, which is, of course, closely related to what we're trying to do with pattern recognition, it's been standard technology to treat vision as if it were like the television screen. You simply scan over, you have all these pixels one right after another, and you keep doing that, then you do some software manipulation, and presumably you recognize patterns. But this is not at all the way the human vision system works. The human vision system, if I say it roughly, takes very narrow snapshots of the environment, quite narrow, and then makes a quick jump to some other part. And so if you're looking at a picture, you see this little bit of the picture, then it moves, and you see this little bit of the picture, and so on. These are called saccades. And moreover, those movements are not random. They are controlled by what your central nervous system is saying. So they pick out what we could call roughly salient points of the picture. This is something we don't have the faintest idea about how to do this in terms of computer terms right now. There are the people that study saccades, and there are such people in neurophysiology, have almost no computer models of this process. How we put that all together so that we have this subjective feeling that we see the whole room is a real mystery. But one can quickly convince oneself that some of the hard problems in pattern recognition depend on this ability. Okay. Mode of operation. Most of what we know about now in terms of machines and the way we think about things are as if we were routing messages or doing switching or running small subroutines. The central nervous system doesn't work that way at all. It's largely autonomous. What's going on is a tremendous, continuous circulation of neural pulses in there, recirculating, reverberating all the time. And the input to that system is largely just modulating what's already going on. Now, we know this subjectively, but we only see a very level, top layer of this system. What goes on depends tremendously on what's going on underneath the so-called conscious part. This recirculation and reverberation is just incredible. And even when we go to sleep, it's still going on. So what goes on is much more something like a modulation of an ongoing activity. It's not rerouting messages that says, when I see this input, I'll do this action. And finally, if we look at how this system works and try to think about it a bit, we know that what we do is mostly in terms of metaphors, analogies, and so on. One of Doug's favorite points, not a matter of Boolean logic. It's rare that we go about things in that way. Okay. All of these are